Lesson 9. Strain energy and the stress-strain curve. Every time you load a member elastically, it stores the work you put in, like a spring. That stored work is the strain energy, and it's just the area under the load deflection line. Scale it per unit volume, and it becomes the area under the stress-strain curve, which also tells you two material properties the exam loves: resilience, the elastic energy to yield, and toughness, the total energy to fracture. One picture ties all of it together. Here's the problem. A steel bar, 1 meter long, 500 square millimeters, pulled with 100 kilonewtons. Given the modulus and the yield strength, find the total strain energy stored in the bar, the strain energy density at the working stress, and the modulus of resilience, the elastic energy per unit volume the material can soak up before it yields. 3 energy answers, 1 axial load. The trick is keeping total energy and energy per volume straight. Concept 1. Strain energy is stored work. Push a load that stretches the bar. In the elastic range, the load rises in a straight line with the stretch. So the work you do is the triangle under that line. 1/2 load times deflection. Substitute the elongation formula from lesson 1 and it becomes P²L over 2AE. Same triangle, 2 ways to write it. The units are energy, and the bar returns all of it on release, just like a spring. Concept 2. Strain energy density. Take the same stored energy and scale it to a unit of material, and it becomes the area under the stress-strain line. 1/2 stress times strain. Apply Hooke's law, and that's sigma squared over 2E. It's the total energy of the previous slide divided by the bar's volume, a standard definition, so it carries no separate pill. Watch the units. This is energy per volume, not a stress, even though the number comes out in megapascals. Concept 3. The stress-strain curve. Pull a specimen to failure, and the curve tells the whole story. First, a straight elastic line, whose slope is the modulus of elasticity, up to the proportional limit, where linearity ends. Just past it is the elastic limit, the last point that springs back with no permanent set. Then the yield point, where plastic flow takes off, and the material strain no longer recovers. The curve climbs to the ultimate strength, its peak, then falls to fracture, the Handbook's breaking point. Proportional limit, elastic limit, yield, ultimate, fracture. That's the map. Concept 4. Resilience versus toughness, the pair the exam loves to swap. Resilience is the area under the curve up to yield, the elastic energy the material stores and gives back. And it has a clean formula, yield stress squared over 2E. Toughness is the total area all the way to fracture, elastic plus plastic, the total energy absorbed before it breaks. Resilience is a thin elastic sliver. Toughness is the whole area. A spring is resilient. A steel that stretches far before snapping is tough. Setup. Write the load, length, area, modulus, and yield strength, then leave blanks for the working stress, the stretch, and the 3 energy quantities. Commit to newtons and millimeters up front. Then the load times the deflection comes out in Newton millimeters, which are millijoules. The one check before anything else. Confirm the working stress is below yield, so the bar is elastic, and every formula here is valid. Solve. Part 1. Working stress is load over area. Below yield, so the bar is elastic, and we're clear to use the energy formulas. The stretch is PL over AE. Then the strain energy is 1/2 load times stretch. Cross-check with P²L over 2AE. Same answer. 2 routes, 1 number. If they disagree, a unit slipped. Solve. Part 2. Strain energy density at the working stress is sigma squared over 2E. The modulus of resilience is the same formula evaluated at yield instead, a material property, independent of the current load. And the cross-check that keeps density and total energy straight, multiply the density by the loaded volume, and it returns the total strain energy exactly. Notice resilience comes out 4 times the working density, because yield is twice the working stress, and energy scales as stress squared. Final answers. The bar stores 50 joules of elastic strain energy under this load. The energy density at the working stress is 1/10 of a megajoule per cubic meter, and the modulus of resilience, that ceiling before yield, is 4/10. Density times volume returns the 50 joules, our consistency check. Toughness, the total energy to fracture, is much larger still, the entire area beyond yield, but there is no tidy formula for it. Traps. 3 ways this topic bites. 1. Resilience is not toughness. Resilience is the elastic area up to yield, a thin recoverable sliver with a clean formula. Toughness is the total area all the way to fracture, elastic plus plastic. Don't swap them. 2. Energy density is per unit volume, not a stress. It just happens to share the unit megapascal. Multiply by the volume to get an actual energy in joules. 3. Proportional limit, elastic limit, and yield are 3 distinct points. The modulus only describes the straight line up to the proportional limit. Quick recall. Strain energy is the area under the load deflection line, 1/2 load times stretch, or P²L over 2AE. Scale it per unit volume, and it's the area under the stress strain line, sigma squared over 2E. Multiply density by volume to recover the total. Resilience is that density evaluated at yield, the elastic area. Toughness is the whole area to fracture, and the curve runs proportional limit, elastic limit, yield, ultimate, fracture, with the elastic slope equal to the modulus. Keep total energy and density apart, and this topic is quick points. Next up, Lesson 10. The Week 1 Capstone, Exam Strategy and Fully Worked Mechanics of Materials Problems. We've built the whole toolkit, axial through combined loading, and now strain energy and the stress-strain curve. Next, we put it to work under time. How to read a question fast, choose the right formula, sidestep the traps we flagged all week, and verify before moving on. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.